Okay, let's unpack this. Remember that feeling. Playing a game, getting totally lost in it, and you almost didn't realize you were, actually learning something.
Mm-hmm. That's the magic, right? That's the allure of game-based learning. It promises so much.
It really does. Turning dull drills into, like, adventures, making tricky concepts just click in a way maybe a textbook doesn't always.
Yeah.
But, it's not always quite that simple. Sometimes the fun stuff, the game elements themselves, can actually kind of trip up the learning.
That's exactly right. And especially for you, I mean, someone with a background in elementary education, you're always on that quest.
Yeah.
Right? Looking for tools that really work.
Constantly. Ways to make learning spark those aha moments.
Yeah.
But without, overwhelming the little ones.
Right. And what's so fascinating here is, well, digital games offer these incredibly rich, interactive experiences, no doubt.
Totally.
But they also bring these unique challenges, often really subtle ones, for a learner's brain, especially a young learner's brain.
Absolutely. So today, we're diving deep into some really fascinating research. It's like our guide here. Multimedia design principles and game-based learning.
Mm-hmm.
Our mission, really, is to figure out how games can be designed to genuinely support learning, not just, entertain. We want to pull out the key insights, the practical stuff, to help you navigate this field.
Especially with elementary students in mind.
Exactly. It's about being able to tell the difference, right, between the games that are truly educational and the ones that are just flashy.
Yeah, discerning the good from the maybe less effective. And our main guide today is this fantastic chapter by Brian Elson and Yansoo Kim.
Also called Multimedia Design Principles in Game-Based Learning. Makes sense.
It does. It's part of a major handbook on the subject. And it pulls together wisdom from really big names in the field. Think Richard Mayer, James Paul Gee, David Williamson Schaffer.
Okay, solid sources.
Very solid. It gives us a really robust way to think about effective game design for learning.
Okay, so let's kick things off. Let's talk about the appeal, because it is incredibly appealing game-based learning.
Oh, absolutely.
The experts say, when they're designed well, these digital games can offer these amazing visual and auditory experiences. They foster what's called active, situated learning.
Mm-hmm.
But situated learning, what does that really mean for a teacher, practically? How's it different from, say, just a worksheet problem?
That's a great question. It's a crucial difference. So when researchers like Gee or Schaffer talk about situated learning, they mean learning that happens inside a context that feels real. That makes sense.
Okay. Like the real world.
Kind of mirroring real-world challenges, yeah. You're not just reading about something abstractly, you're doing something with it in a simulated world. You make decisions, you see the consequences right away.
Oh, okay.
It's applying knowledge, practically, so it moves way beyond just, memorizing facts for a test. It's about application, solving complex problems, learning by doing, basically, but in this really engaging digital space.
Right. And for you, working with elementary kids, that situated learning idea is just so powerful.
Absolutely.
Imagine like a digital game where first graders practice shopping, a virtual grocery store.
Mm-hmm. Great example.
They're not just looking at numbers on a page, right? They're picking up virtual apples, counting virtual coins, making change like they're really there.
Feels real but safe.
Exactly, safe space. And they're using their math skills in a context that's actually fun. It's relatable. They learn about money not as like abstract symbols, but as a tool, something you use.
Which is a much deeper understanding. That connection between abstract concepts and the real world, that's gold for young learners.
Totally. Okay, so the potential is huge. Engagement, deeper understanding, got it. But now, the peril part.
Yes, the flip side. Because here's where it gets tricky. While all that richness, the great visuals, the immersive sound is often seen as a huge benefit. It can also be a major challenge. Plass, Homer, and Kinzer pointed this out back in 2015. There's this tension. Designers want realism, sensory richness, to draw players in.
Sure, that makes sense.
But that very richness can sometimes just flat out overwhelm a learner's ability to actually process the important stuff. It's a really delicate balance.
So the very thing that makes them cool can actually hinder the learning.
Precisely. Think about it. Players are often trying to process tons of sensory info sites, sounds, plus make split-second decisions, figure out maybe complex controls.
Right, like a button mashing while trying to remember a science fact.
Exactly. And grapple with the actual curriculum content they're supposed to be learning. All at the same time.
Whoa. Yeah, that's a lot.
Their brains are just working overtime on everything. It's like
Yeah.
juggling, 5 flaming torches while trying to read Shakespeare.
Okay, yeah, not going to end well.
Probably not. And this leads to what scientists call cognitive overload. Imagine your brain's working memory, its processing power, is like RAM in a computer. Limited capacity.
Okay.
If you open too many demanding apps or apps with lots of background junk running, what happens? It slows down, it freezes.
Crashes. Been there.
Right. Same idea with our brain's learning. Too much info, too many distractions presented badly, the system gets overloaded. Learning just stops.
And you mentioned a specific type, extraneous load.
Yes, extraneous cognitive load. That's the mental effort wasted on irrelevant stuff, unnecessary information. It's the processing that doesn't help you learn the actual goal. It's the noise.
Ah, the noise. That makes sense. And that's what these multimedia principles are trying to cut down.
Primarily, yes.
Yeah.
Reducing that noise so the real signal, the learning, can get through.
Okay, that makes so much sense for elementary kids. They're captivated easily, but also, man, distracted easily.
Oh, yeah.
So beyond just flashing lights, what's a subtle way a game might add that noise, that extraneous load? Like, say, a kindergarten game for letter sounds. Okay, too many lights, sounds, crazy animations. Yeah, that's obvious overload. But what if the background is just super detailed, like a beautiful, realistic city street?
Even if it's not flashing.
Right. Does just processing all those buildings and cars while trying to focus on the letter B, does that add extraneous load?
Absolutely it can. Even static complexity requires processing. Their little brains are working hard on the distractions, processing the background details, not just the letter. It's like trying to teach reading, as you said, in the middle of a carnival.
The carnival analogy, perfect. I feel like I've tried teaching in a carnival sometimes, even without screens.
Huh. I think every teacher has felt that way. It's a fundamental challenge of attention, not just games.
Right.
So to design better, avoid that cognitive carnival, we need to understand this cognitive load theory properly. Sweller, Van Marienboer, and Pass laid it out brilliantly back in '98. 3 types.
Okay, 3 types. Let's break them down.
First up, intrinsic load. This is the inherent difficulty, the mental effort needed just to understand the material itself.
Okay, the core challenge.
Exactly. It depends on how tough the subject is naturally, but also really importantly, on what the learner already knows, their prior knowledge.
Ah, okay, so it varies.
Totally. For a total beginner learning code, a simple programming task has super high intrinsic load. It's all new, abstract concepts, lots of mental heavy lifting required just to get it.
Okay, so for my second grader, just learning multiplication, 7 times 8, that's high intrinsic load for them.
Definitely. New concept, building those connections, their working memory is firing on all cylinders, just trying to understand the operation, retrieve the answer.
But for my 5th grader, same problem, 7 times 8, much lower intrinsic load.
Right. They've practiced, maybe even automated, they can recall it quickly, freeing up that mental RAM for, say, a complex word problem using multiplication.
Got it. So intrinsic load is relative to the learner. Makes sense. What's next?
Next is extraneous load. This is the one we were just talking about, the bad load.
The noise.
The noise, exactly. Mental effort imposed by stuff that's irrelevant or just unnecessary, presented badly. Poor instructional design, basically, whether it's a game, textbook, whatever. This is the load that multimedia principles are really targeting in games. Yeah. Trying to slash this down. It just drains mental resources without helping learning.
So back to the multiplication game. If there's a distracting dancing robot in the background,
Extraneous load.
or flashy fonts constantly changing,
Extraneous load.
irrelevant sound effects.
Yep. All extraneous. The kid's brain has to process all that extra visual auditory junk, pulling attention away from the actual math, like loud ads popping up mid-lesson.
Every pixel, every sound that doesn't directly help potentially adds to that burden. Wow. Okay, 3rd type.
The 3rd type is germane load. This is the good kind, the productive effort.
Okay, finally some good news.
Huh. Yes. This is the mental work involved in actually processing the information deeply, building those strong mental models, like creating a clear map in your head of how something works.
Ah, okay. Making sense of it.
And developing skill automation. When something goes from needing intense focus, like learning to tie shoes, to becoming automatic.
Yeah, like riding a bike. Don't even think about it eventually.
Exactly. That frees up your cognitive resources for higher level thinking. That's germane load at work. It facilitates real learning, real understanding.
So the goal is low extraneous load, right? Get rid of the noise. Keep intrinsic load manageable, appropriate for the learner.
Right.
And then you can maximize this germane load, the good stuff.
Precisely. When the intrinsic load is right and the extraneous load is minimized through smart design, the learner can dedicate their precious mental energy to that germane load, actively building knowledge, making connections, deepening understanding.
That's the sweet spot. Okay. So if our multiplication game is clear, concise, minimal distractions,
Yep.
the child's brain can focus its germane load on understanding multiplication, memorizing facts, really getting it.
They're working on the right things,
Yeah.
not fighting distractions.
You got it. So applying these multimedia principles, the big goal is chop down extraneous load to boost germane load, make learning truly effective.
That's the core idea. Strategic design, like a chef making sure every ingredient serves the final dish, not just throwing things in.
Okay, so if we want to be those master chefs, how do we actually do it? How do we design or pick games that really work for elementary kids?
Well, the good news is we have guidance. Researchers like Mayer and Moreno, way back in 2003, developed these fantastic multimedia principles.
Right, you mentioned them. Guidelines.
Evidence-based guidelines, yeah, for arranging text, pictures, sounds, animations to actually support learning. They're specifically aimed at lowering that extraneous load and supporting germane load. It's like a roadmap.
A roadmap for effective design. I like that.
And they come from understanding how our brains process information, especially visuals and sounds. Dual coding theory, basically. It's not just about making things look cool or fancy.
It's about cognitive efficiency.
Exactly. Designing environments that work with how our minds learn best. Minimizing mental friction, maximizing understanding, working with the brain, not against it.
Okay, and the chapter groups these principles.
Into three main buckets based on what they're trying to achieve instructionally. First, reducing extraneous processing, the noise reduction we talked about. Second, managing essential processing, making the core stuff easier to grasp.
Okay.
And third, fostering generative processing, encouraging that deeper understanding, knowledge building.
Got it. Reducing noise, managing the core stuff, building deep understanding. We'll hit each one.
Yep. We'll look at each, see how they apply in games, what the research says, and really importantly, how you can use this thinking for your elementary classroom.
Perfect. Practical is key.
Absolutely. And to make it concrete, the authors of our source chapter talk about their own work, the SAVE VA Science project.
PASSI e-science.
Yeah, it was this big effort creating game-based environments for middle school science assessment. Really cool stuff. Shows how these principles play out in real game design.
Okay, so real-world examples, like what?
Well, one specific game was called Sheep Trouble.
Sheep Trouble. Sounds ominous.
A little. Students basically played science detectives trying to figure out why a virtual herd of sheep was getting sick.
Okay. So the goal wasn't just fun, it was assessing their understanding of what?
Evolution and adaptation, actually.
Yeah.
Complex stuff. But instead of a multiple choice test, it was this dynamic simulation.
Okay. Learning by doing again?
Exactly. In Sheep Trouble, students had to do real science inquiry stuff. Talk to virtual characters like a concerned farmer.
Okay.
Use interactive tools, measure sheep legs, record weights, check age and gender, then develop hypotheses about why they were sick, test them out.
Wow, that sounds pretty involved.
It was. And it provided this really rich context for applying these design principles because students were actively dealing with complex info, making choices, seeing results, not just passively watching.
Okay, Sheep Trouble was middle school. But I can totally see adapting that for younger kids, like farm helpers, little kids helping figure out why a virtual plant isn't growing.
Great idea.
They check the soil, the water, the sun level, teaches basic plant needs interactively, scientific observation, problem solving, but in a safe, fun way.
Exactly. The core idea, solving problems in a simulation driven by interaction, works across age groups. That's why these principles are so useful.
All right, so cognitive overload, especially the extraneous noise, is the enemy. How do we fight it? How do we design or choose games that strip away the unnecessary mental work?
Okay, first set of principles, reducing extraneous load. The first big one here is the signaling principle.
Signaling, okay.
It just means people learn better when you use cues, visual or auditory, to highlight the essential stuff. It's like a cognitive spotlight.
Directing attention.
Exactly. Directing attention where it needs to go, reducing the effort of figuring out what to focus on. Super important in games where there's often a lot going on visually.
And the research supports this.
Oh, yeah. In that Sheep Trouble game, they tested this. Added subtle visual signals like glowing arrows or highlights over the sheep you needed to measure or the characters you needed to talk to.
Okay, little prompts.
And the students who got those signals, they reported feeling less mentally overloaded, less taxed. And crucially, they interacted more with the important parts of the assessment. They knew where to look, what to do. Focus their energy on the science, not hunting for clues in the interface.
Okay, so signaling helps focus. But you mentioned a nuance.
Right. The follow-up study, different setup, more visually complex. Computer science students instead of middle schoolers didn't show the same strong benefit.
Why not?
The guess was these older students were already experts, basically. They didn't need the same hand-holding signals. So it suggests signaling is most powerful when the environment is complex, or, and this is key for us.
When the learner is a novice.
Exactly. For a developing brain, clear guidance is invaluable.
Okay, huge practical takeaway for elementary. Think about like an online find the letter game for preschoolers. Instead of just a jumble of letters, maybe a subtle glow around the target letter, find the A, boom, their eyes go right there.
Perfect example.
Or in a virtual art studio game, if they need to click the paintbrush, maybe it pulses slightly, guides them without being overwhelming. Purposeful cues. Keeps them on task.
Precisely. Especially important when attention can wander so easily. Okay, next principle, redundancy principle.
Redundancy sounds like something we want to avoid.
Usually, yes. In traditional learning, like a lecture with slides, research shows people learn better if words are only spoken, not spoken, and printed on the screen at the same time.
Why is that?
The theory is processing the exact same info in two ways at once, listening and reading simultaneously, forces your brain to try and integrate them, which is actually more work, more extraneous load than just processing one stream.
Okay, interesting. Don't double up identical info.
Generally.
Okay.
But here's a twist, really relevant for games, especially with younger kids.
Uh-oh. Nuance again?
Always nuance.
Yeah.
In the Design a Plant game research, they found students who heard narration or had both narration and text learn better than students with only text.
Wait, so narration plus text was okay there? That seems to contradict the redundancy principle.
It does, initially. But the thinking is in exploratory dynamic games like that one where the visuals are complex and changing. Narration might grab attention better. And critically, it lets the learner keep their eyes on the game, on the action, the visuals, instead of splitting attention between looking at the game and reading text.
Ah. So the audio carries the instruction, freeing up the eyes for the game itself.
Exactly, especially if the visuals are demanding. The auditory channel handles the words, the visual channel handles the game world. Less competition.
Okay, this is super important for early readers. For a game teaching new words, if the word cat appears, hearing a narrator say cat is key for connecting sound and symbol.
Absolutely crucial for literacy.
But this idea that only spoken words might sometimes be better than spoken and printed, that's fascinating. It suggests in visually busy games, maybe just rely on the audio guide sometimes.
It's a possibility to consider. It means we need to be really selective. When do we add text if we have a good narrator? Think about the age, reading level, the visual complexity of the game. Avoid that visual competition.
Right. Always aim to reduce that load. Okay, what's the third one in this category?
Third one is the immersion principle. This one challenges a big assumption.
Okay, I'm ready.
It basically says people do not necessarily learn better just because a game is in realistic 3D virtual reality compared to simpler 2D.
Whoa, hold on. Really? But VR, immersion, isn't that the whole point, making it feel real?
That's the intuitive thought, right? More immersive, more realistic, must be better for learning. But the cognitive load argument comes back.
How so?
Think about a super realistic 3D world. A young learner has to process spatial relationships, depth, complex models, textures, lighting, maybe tricky 3D navigation.
Yeah, okay, that is a lot more to process than a flat image.
It is. And if all that added realism just becomes more visual noise, more extraneous stuff for the brain to sort through, it can actually work against learning, not for it.
Wow. So the cool factor doesn't equal learning factor.
Not automatically. Those Design a Plant studies, they compared a 3D VR version with a standard 2D desktop version. The 3D VR gave a stronger sense of presence, sure. Students fell more there. But it didn't lead to significantly better learning, retention, or transfer. Sometimes later studies even found the 2D versions led to better retention.
That is a massive takeaway. Seriously, we always think more tech, more immersion, better learning.
It's a pervasive myth.
So for elementary classrooms, this is huge. It means a clear, uncluttered, well-designed 2D game might be way more effective than some dazzling 3D world that just distracts them.
Especially for kids still developing visual processing skills, spatial reasoning. They can get overwhelmed easily by too much sensory input.
Simplicity can be powerful. Clarity. Intentional design where every visual element helps, doesn't just decorate.
Exactly. You don't need a $1 million VR setup to teach counting. A thoughtful 2D app can be fantastic, precisely because it minimizes that extraneous load.
Okay, so I've cleared the noise, reduced the extraneous load. We've got simpler, clearer signals, maybe avoided unnecessary 3D realism. Now what? How do we make sure kids are efficiently processing the actual important stuff, the core learning?
Right. Now we focus on managing the essential processing, making sure the intrinsic difficulty, the core challenge, is handled smoothly.
Okay, managing the essentials. How?
First principle here is the pre-training principle. Big one.
Pre-training. Sounds like what it is. Train beforehand.
Basically, yeah. People learn better if they get some training on key concepts before they jump into the main learning experience, like the game.
Why does that help?
Well, if they already have a basic grasp of key terms, core ideas, then during the game, they can use their limited mental energy for connecting ideas, applying concepts, solving problems within the game.
Instead of trying to figure out what a word means while also trying to play the game?
Exactly. You front-load some of that intrinsic difficulty. So the game becomes a place for applying and deepening understanding, not just trying to figure out the basics.
That makes so much sense. It's like prepping the ingredients before you start cooking the main dish.
Perfect analogy. And good teachers do this instinctively all the time, right?
Huh.
Activate prior knowledge.
For sure. Does the research back this up in games too?
Yep. There was a profile game study learning about geological features. Students who got visual pre-training basically shown pictures of what trenches or ridges looked like before playing.
Yeah.
They solved way more problems on the follow-up tests. They weren't struggling with definitions inside the complex game environment. They had the foundation.
So it freed up their cognitive capacity to focus on the game's tasks, applying the knowledge, not just acquiring it.
Exactly. Applying, synthesizing, not getting bogged down by basics.
Okay, this is super practical for the elementary classroom. Like if you're using a fraction game, you don't just throw them in cold. You do a quick mini lesson first. Okay, team, remember numerator on top, denominator on the bottom. Fractions are parts of a whole. Today's game uses this.
Right. Activate that prior knowledge, maybe show a quick visual.
Yeah. It prepares their minds, lowers that initial intrinsic load in the game, lets them focus on the game's challenges, not basic definitions, sets them up for success, makes the game a practice tool, not a confusion zone.
Precisely. Okay, second principle for managing essential processing, the modality principle.
Like different modes, sound, visuals.
Yep. It's related to redundancy, but slightly different focus. This one specifically looks at instructional info within games. It suggests people learn better when instructions are spoken, not printed.
Spoken better than printed. Why?
Again, it's about freeing up the visual channel. If the instructions are spoken, your eyes can stay focused on the animations, the game action, the visuals that are key to understanding what's going on or what you need to do.
Ah, okay. So redundancy was about avoiding identical info in both modes. Modality is about choosing spoken over printed for instructions, especially if there are important visuals happening.
You got it. That's the key distinction. And again, Design a Plan showed this. Students who got explanations via narration remembered more, did better on transfer tasks. Their eyes were free to process the complex plant designs.
Parallel processing again. Ears handle words, eyes handle visuals, less competition.
But always a but.
Bring on the new one.
A study with a collaborative game, Simlandia, where students worked together. They compared text chat versus voice chat for team communication.
Okay. Voice chat seems easier, faster.
It was. Voice chat definitely reduced the communication cognitive load, easier to talk.
But did it lead to better learning of the actual content?
Not necessarily in that study. Making communication easier didn't automatically mean they learned the core science concepts better. Maybe formulating clear verbal instructions still takes significant mental effort, just a different kind than decoding text.
Huh. That's really interesting for elementary classrooms, especially with collaborative games popping up.
Right.
So for like a phonics game explaining a rule, a clear, friendly voice narrating is probably way better than a text box a young kid might struggle with or just ignore.
Almost certainly.
But for group work in a game, voice chat might feel easier for them to talk, sure. But maybe text chat, even though it's slower, forces them to be more explicit, think more carefully about what they type, maybe even help spelling.
That's a really insightful point. It could force more reflection, more precise articulation. It's a trade-off. You need to think about the specific goal, the game, the kid's age. Sometimes a little productive struggle in one area frees up load elsewhere.
Okay, we've reduced noise, managed the core info load. Now for the really deep stuff, fostering generative processing.
Okay.
This is about getting kids to really think, right? Build those strong mental models, make it stick.
Exactly. This is where true understanding happens. Moving beyond just receiving information to actively constructing knowledge.
How do we encourage that in a game?
First principle here, the self-explanation principle.
It's self-explanation.
Explaining to yourself.
Pretty much. Learners understand more deeply when they're prompted to explain their thoughts, their decisions, their actions during the game.
Why does that help?
The act of explaining forces you to process the information actively. Connect it to what you already know. Identify gaps in your own understanding. Make your thinking explicit.
Ah, like thinking out loud, but maybe internally or through a prompt? Right. It encourages deeper cognitive engagement, really solidifies the learning. It moves you from just doing the steps to thinking about why you're doing them.
This is such a powerful teaching strategy. Teachers ask, why did you do that? All the time.
Absolutely. And it works in games, too. The circuit game study, learning about electrical circuits.
Yeah.
Students who had to select reasons for their answers explain why they chose a component. They outperformed students who didn't get that prompt. Learned faster, too.
Because they weren't just guessing, they had to justify it, which meant engaging with the actual circuit principles.
Exactly. Creates this metacognitive loop, thinking about your own thinking. Incredibly valuable for finding misconceptions, building solid understanding. It's the difference between memorizing Ohm's law and understanding how electricity actually flows.
Okay, how does this look in an elementary game? Say, building simple machines.
Okay, after they place a gear or a lever, maybe a prompt pops up. Why did you choose that gear size? Or how will this lever help lift the block?
Could be multiple choice reasons, or maybe prompt them to explain out loud to a partner?
Both could work. Or in a virtual field trip game, after watching a squirrel bury a net. What do you think the squirrel is doing? Why? What does that tell us about squirrels? Pushes them beyond just observing to articulating their reasoning. Turns passive watching into active thinking.
Love it. Okay, what's next for generative processing?
Closely related, and just as important, the explanatory feedback principle.
Explanatory feedback, not just right or wrong.
Exactly. That simple feedback gives very little learning value. It doesn't tell you why or how to fix it.
Just leaves you guessing or frustrated.
Whereas explanatory feedback helps you process the material more deeply. Again, in that circuit game.
Yeah.
Feedback that showed the right answer and explained why it was correct, maybe pointed out the flaw in their thinking, led to much better transfer, faster learning than just correct or incorrect.
The why is crucial. It bridges the gap between making a mistake and actually learning from it.
Totally. It helps learners pinpoint their misconceptions, adjust their mental models, turns mistakes into powerful learning moments, guides them towards understanding.
Okay. Elementary math facts game. Kate answers 3 to 2 plus 2. Instead of just BUZZ, wrong.
Yeah. What could it say?
Maybe. Not quite. 2 plus 2 means 2 groups of 2. Imagine 2 apples, then 2 more apples. Try counting them.
Nice. Or
close. Maybe you added 2 plus 1. Remember, 2 plus 2 means adding another 2. That makes 4. Look at your fingers. Provides immediate, meaningful insight. Guides them. Doesn't just shut them down.
That's powerful feedback.
Yeah.
Okay, next, the prompting principle.
Prompting. Like nudging them.
Exactly. Encouraging learners to reflect on their learning during the game. Nudging them to think about underlying principles, bigger connections, how this task fits the overall goal, not just mindlessly completing levels.
Stepping back and processing.
In the circuit game, giving students paper-based aids like guiding questions or things to think about help them perform better and feel the content was less difficult.
Interesting that it was paper-based. Doesn't have to be in the game itself.
Doesn't have to be. But interestingly, the study found high-performing students benefited more from these prompts.
Really? Why is that?
Suggests that prompts work best when learners already have some foundation. They can then use the prompt to organize their thoughts, connect new info, really make it their own. If they're totally lost, a prompt might just add more confusion.
Okay. So prompts help consolidate understanding for those ready to reflect. How would this look for elementary?
Could be built in or supplemental, like in a digital story writing game. Periodically, maybe a prompt. What challenge is your character facing now? How might they solve it?
Or what lesson did your character learn here? Makes them think about story structure.
Exactly. Or a virtual science experiment. What variable are you changing? What do you predict will happen? Why? Encourages metacognition, deeper engagement, connecting game actions to bigger ideas.
Got it. Okay, what else helps build deep understanding?
The personalization principle. This one's about tone and connection.
Personalization, making it personal.
Yeah. People learn better when games use a conversational, personalized style. Words, images, making it feel like the game is talking to them, not at them.
Like using you.
Exactly. Studies with Design a Plant showed using you like your plant needs water instead of the plant needs water led to better transfer and retention. That simple shift makes a difference.
And the avatar thing. In sheep trouble.
Right. Letting students customize their avatar's look and name. That correlated positively with motivation, how well they thought they did, engagement. It was their character, their mission.
Okay, this is huge for engagement, especially with little kids.
Totally. It taps into the social aspect of learning. Feels less like a machine, more like a friendly guide. Builds ownership, relevance, motivation.
So when a game character says, "Hi, Sarah, ready to explore the rainforest with me," instead of "the user will now explore."
Much more connecting. Allowing kids to choose their avatar outfit, maybe a little pet helper, boosts their feeling of ownership hugely. Makes the learning journey theirs. Even subtle language shifts matter.
Definitely keeping that in mind.
Okay.
Okay, next.
The image principle. This looks at pedagogical agents, those on-screen helper characters. Just having their picture there help learning.
Does it? Seems like it might make it feel friendlier.
The theory is it fosters a social connection, yeah. But research with Design a Plant was mixed.
How so?
An animated agent could increase interest, maybe help with tricky problems just by being there socially. But the narration from the agent, what it said, seemed to be the main driver of learning outcomes, not just its picture being on screen.
So it's more about what the helper does or says than just how it looks.
Seems that way. The visual presence might add a social cue, but its active role in explaining and guiding is what really impacts learning. Just having a cute character standing there passively doesn't do much.
Okay, practical takeaway for elementary. A friendly, consistent narrator's voice is probably more important and maybe cheaper than a super fancy animated character that doesn't do much.
Likely, yes. If you do have an animated helper, make it interactive. Its actions should link to the learning, illustrate the concepts, not just be decoration. Every element should contribute, not just look nice.
Right, function over just form. Okay, one more.
Last one in this category, the narrative theme principle. This one's another counterintuitive one.
Okay, hit me. Narrative. Like story. Strong stories help learning. More engaging.
That's the intuition, right?
Yeah.
Rich story equals motivation equals better learning. But the actual evidence, surprisingly mixed, sometimes even the opposite.
Whoa, opposite how?
Studies with games like Crystal Island or Cache 17 found students playing the versions with really rich, complex narratives sometimes had lower transfer scores.
Lower? They couldn't apply the learning as well.
Right. And they reported feeling like the game was harder, took more mental effort than students who just got the core content via slideshows.
No way. Why would a good story make it harder to learn?
The thinking goes back to cognitive load. A really complex narrative. Lots of characters, backstories, subplots can divert mental energy.
Processing the story details instead of the learning content.
Exactly. Your cognitive resources get spent following the plot, remembering who's who, navigating the fictional world, letting focus away from the science or math concepts. It adds extraneous load, ironically.
Wow. Okay, that is a huge surprise. Huge implications for elementary. So while a simple frame story like a quest or mission is probably good for motivation like our farm helper's idea.
Yeah, that provides context and purpose.
An overly complex story like a mini movie plot might actually distract young learners from the core concept.
You very well could, especially with developing attention spans and processing capacity. For elementary, a clear learning goal within a fun, simple context might be way more effective than a complex narrative.
The why of the game, the story shouldn't overshadow the what's the learning. Keep the narrative lean and focused on supporting the learning goal.
That seems to be what the evidence suggests. Sometimes less narrative is more effective for focused learning.
Okay, wow. We've covered a ton of ground. So if we pull all these principles together, what does the ideal, prototypical learning game look like based on this research?
It's an interesting picture. Based purely on these findings, you might imagine something like this. A 2D game, probably without a complex narrative.
Okay, 2D, simple story.
Players guide avatars, They've maybe customized a bit. Before they start, they get clear pre-training on key concepts.
Pre-training first.
In the game, important objects or areas have clear visual signals. Players get frequent explanatory feedback, the why behind right or wrong answers.
Okay.
They're prompted to explain their choices, maybe reflect periodically, and the crucial instructions, mostly delivered through narration, minimal text, cluttering the screen.
So 2D, non-narrative, customized avatar, pre-training, signaling, explanatory feedback, self-explanation prompts, reflection prompts, narration over text.
That's the synthesis, yeah. But it immediately highlights this tension. As the source material point out, this prototypical design, well, it starts to look less like a typical commercial game and maybe more like a really well-structured interactive instructional system or tutorial.
Yeah, I see that. Less gamey, maybe.
Possibly, which raises big questions. What is a game in an educational context? Does it have to feel like a commercial game to be effective? Or can optimal learning sometimes mean sacrificing some of those traditional game elements like narrative or immersion for cognitive efficiency?
That's a really deep question. Does effective learning design sometimes look different from fun game design? And where's the sweet spot? Crucial for teachers thinking about this.
Absolutely. And we also have to be honest about the limitations of the research itself, which the authors are clear about.
Like what?
Well, the games studied are all over the map. Different designs, different goals, different platforms. A principle that works great in a complex 3D exploration game might be totally unnecessary in a simple 2D math drill. Context matters hugely.
Right, not one size fits all.
And another huge one, the quality of the games themselves. Jim Gee's famous quote comes to mind. I never said bad games are good for learning.
Good point.
Educational games often don't have the budget, the time, the design expertise of commercial games. They might lack core game elements, real challenge, meaningful choices, good feedback loops.
So if the game itself is just bad or boring, then testing these principles on it might not tell us much.
Exactly. You need a reasonably engaging foundation first. A poorly designed game won't teach well, principles or no principles.
Okay, another huge practical point for educators. Don't just grab anything labeled educational. Is it actually a well-designed game too? Does it follow these cognitive principles? Need to be discerning.
Very discerning. And one more big limitation. Study duration. Many of these studies involve playing for like 20, 30 minutes, one session.
Right. Real learning doesn't usually happen that fast.
Exactly. Deep understanding, skill mastery that comes from sustained engagement over time. Weeks, maybe months. You don't master fractions in half an hour.
So, as teachers, we should see these games as tools to be integrated over time, not just a one-off activity.
That's likely where the real power lies. Thoughtful integration into the curriculum, allowing for practice, reinforcement, building complexity over time. It's a tool in the toolbox, not the whole solution.
Got it. Tool, not magic bullet. Makes sense.
But even with those limitations, this research is incredibly valuable. It's evolving, yes, but principles like self-explanation, explanatory feedback, pre-training, personalization, they consistently show real promise. Solid, evidence-based starting points.
And even the negative findings are useful, right?
Right.
Knowing that full immersion or complex stories aren't always better, maybe even detrimental sometimes, that's important.
Hugely important. And knowing that smart design like signaling can help manage load in complex environments. It's about being strategic, intentional, using the right tool for the job.
Not just throwing more tech at the problem.
Precisely. And there's so much more research needed, especially looking at these principles with different age groups, like your elementary students and in different learning settings. Lots more to explore.
Okay, so wrapping up, we've really unpacked this world of game-based learning, seen the potential, seen the pitfalls. We dove into cognitive load, intrinsic, extraneous, germane, and how crucial that is, and explored specific multimedia principles, signaling, pre-training, personalization, explanatory feedback that can really boost learning.
Yeah, the practical tools.
And learned that counterintuitive lesson. Sometimes less is more. A simple, clear 2D game might beat a flashy 3D one for actual learning, especially for younger kids.
It often comes down to reducing that extraneous load.
So the big final thought then, the tension you mentioned.
Yeah, it really leaves us with a question, doesn't it?
Yeah.
If the most cognitively effective game design starts looking more like structured instruction, does that challenge how we think about games for education?
Right. How do we balance making it fun and engaging, feeling like a game, with making it truly effective for deep learning based on these cognitive principles?
Exactly. How can you, as an educator, leverage these principles. Whether you're choosing games or maybe even involved in designing simple ones, how do you find or create experiences that bridge that gap between pure fun, fundamental, lasting learning for every child in your classroom?
Finding that balance, delight, and deep understanding.
That's the goal.
So maybe next time you're checking out a new educational game for sight words or ecosystems or whatever, look past the cool graphics for a second. Ask, does it signal clearly? Does it do any pre-training? Is it personalized? Does the feedback explain why? Does it maybe prompt for self-explanation? Is it helping foster that good, productive, germane cognitive load?
Thinking like a cognitive architect.
I like that. Keep thinking about how to strip away the noise, manage the core challenge, and really help your students build that deep understanding. Make the learning fun, yes, but most importantly, make it stick.